Here's the definition of semialgebra, which we brought up at the end of the previous lecture. So we say that fancy S here, a set of subsets of X, is a semialgebra of sets on X, if and only if it contains the empty set, the full thing, is closed under intersections, and then instead of also being closed under unions, or equivalently, instead of also being closed under complements, we have this condition. So anytime you have a set from S and you delete from inside it another set from S, then the resulting relative complement is a finite union of disjoint things in S. So it might not be in S, but it's a disjoint union of things in S. So like I mentioned last time, the way I like to think about what a semialgebra of sets is that it's like finite unions away from being an algebra of sets. So it's something that's designed, this last condition is designed, so that once you throw in finite unions, then it becomes an algebra of sets. So the next thing we'll do is actually prove that fact, that once you throw in finite unions, it does become an algebra of sets. So here's the next thing we're going to prove. Lemma 1.2.14. Let's say you have any semialgebra S, semialgebra of sets on a set X. Then throw in finite unions. So let this be the collection of finite unions of things in S. Of course, it includes things in S, since those would be the n equals 1 case, where you're just unioning a one thing, right? So this is a superset of S that also contains finite unions of things in S. Then, two conclusions in this lemma. One is that this is an algebra of sets on X. Immediately it follows then, once we prove this, that this is the algebra of sets that S generates. That's because, whatever is the algebra of sets that S generates, it must contain all of these things, right? Because an algebra of sets has to be closed under finite unions. And so if this thing is enough, if just throwing in the finite unions is enough, and this is an algebra of sets on X, then this is the algebra of sets on X that S generates. All right, and number two, it's enough to take pairwise disjoint things in S if you want to build this thing up. So originally what I'm writing here when I define fancy A is unions of any finite unions of things in S, but then down here I'm writing finite unions of things in S that are pairwise disjoint. So what we're saying in number two is this: you can also do it this way. So that's not automatic, right? Like, you could have some things being in here where you can write them as a union of things in S that are not necessarily disjoint, and then if you try to tweak things to make the sets disjoint, then you might worry that the components of the union that you have now made disjoint are no longer things in S. So part two is saying that that's not a worry. All right, so let's prove part one here. So I'm going to do the whole setup in each part. So let's say S is a semialgebra of sets on X. Let's say A is finite unions of things in S. And then we need to prove that A is an algebra of sets on X. And that's all part one is. So a few things to check. One thing we need to check is that it contains these things. I mean, I guess since we're going to check that it's closed under complements, it's enough to ensure that it contains this thing. And yep, that's part of the definition of semialgebra, right? We need to check that it's closed under finite unions. And yep, so these two are just totally obvious. Why is it closed under finite unions? Because it is the collection of finite unions of things in S, right? So if you take a finite union of finite unions of things in S, then by just moving parentheses around, you can see that that is a finite union of things in S. All right, then what's left is closure under complements, and that's what's going to take work. And that's where you're going to see why you have this funky third bullet point here in the definition of semialgebra. It's just whatever was needed to make this part of the proof that we're about to do end up working. Okay, so closed under complements, let's check. So actually first, it'll help to first show that it's closed under intersections. Even though that's, if we can just directly show it's closed under complements, then that's enough that we automatically get closed under intersections from closed under finite unions, right? But it's convenient to pass through intersections. So first we show A is closed under intersections. Finite intersections. Okay, so let's take two things in A. Suppose A1 and A2 are in A. Say A1 is, so each one is going to be a finite union of things in S, right? That's the definition of A. So let's say A1 is S1, 1, union up to S1, n, and A2 is S, the union of these S superscript 2's. And maybe there's n of these and there's m of these, where these s's are all in fancy S. Now our goal is to show that A is closed under intersections. The whole point is to intersect these. So when I intersect these, I get the intersection of two, let me write them like this, two unions. So this one is a union, let's say from I equals 1 to n, and this one is a union from maybe j equals 1 to m. Here I'm putting the S1 i's, and here are the S2 j's. And we need some parentheses. By the way, I noticed in your LaTeX on your homeworks, sometimes for some people, a minority of people, there's not really a distinction between the big union and intersection symbols and the small ones. So like this is a small one, so it's just cap, right? But then this is not cup. This is big cup. It does make a difference because it'll make the size of it appropriate. Like you're seeing, the sizes here are different. And it'll actually also put subscripts and superscripts in the right places, depending on the display mode. Okay, now using our usual distributivity law, think of it like this is a sum, and that's a sum, and that's like multiplication. And then you get a double sum, kind of. This is how I think of the distributivity law. So you've got this double union, which is just a big finite union of these intersections. And these, sorry, this is a J. So these intersections, these are all things in S, right? Since S is a semi-algebra of sets on X, and a semi-algebra is closed under intersections. So these are always in S. And so therefore, this is in A. Right, because it's a finite union of things in S. A is by definition the set of finite unions of things in S. Alright, so we have successfully verified that fancy A is closed under intersections. Now let's address complements. So let A be something in fancy A. And let's say A is S1 union up to Sn, where S1 through Sn are things in fancy S. Now let's take the complement. So it's enough to only consider global complements when we're showing something as an algebra of sets. So I can just do this. So let's check this global complement. By global, I don't know if that's the correct terminology. Maybe absolute complement as opposed to relative complement. I just mean X, the full space, delete this, rather than taking two arbitrary things in fancy A and then doing one complement the other. This is sufficient to check. And what do I get? So I'll get X delete this union. So by De Morgan's law, I have X delete this, intersect all the way up to x delete this. And what's going on with these? Well, each of these, so this is finally where the definition of semi-algebra can shine. Each of those is a finite union of disjoint sets in the semi-algebra, right? Each is a well, let me just summarize. Each is a finite union of things in the semi-algebra, right? So therefore each is in fancy A. A is the set of finite unions of things in the semi-algebra. Now, we just got done showing that fancy A is closed under intersection, and so therefore this, which is an intersection of things in fancy A, is in fancy A. It's not fancy enough. There. So that's it. That's it. That's the last thing we needed to check, closure under complements. So then this really is an algebra of sets on X. And we have proven 1. And remember that along with that comes this conclusion. So I don't have a very nice notation. I never introduced one for the algebra of sets generated by something. I have a nice notation for the sigma algebra of sets generated by S, like this. I would call it sigma of S. But I don't have a nice notation for just the plain algebra of sets. So that's why I'm writing it in words. The algebra of sets that S generates is equal to A, simply finite unions of things in S. All right, let's prove 2 in the next video.